I'd like to welcome everybody to the monthly speaker series for the Johns Hopkins University Institute for Assured Autonomy, or as we call it, the IAA. For those of you unfamiliar with the IAA, you can learn more by visiting the website at iaa.jhu.edu. My name is David Silverberg, and I will be introducing the speaker. So it is my pleasure and privilege to introduce Dr. James Hendler. Dr. Hendler is the director of the Institute for Data Exploration and Applications at the Tetherless World Professor and the Tetherless World Professor of Computer, Web, and Cognitive Sciences at RPI. He also heads the RPI-IBM Center for Health Empowerment by Analytics, Learning, and Semantics. Dr. Hendler has authored over 400 books, technical papers, and articles in the area of the semantic web, artificial intelligence, agent-based computing, and high-performance processing. One of the originators of the semantic web, Dr. Hendler was the recipient of the 1995 Fulbright Foundation Fellowship, is a former member of the U.S. Air Force Science Advisory Board, and is a fellow of the AAAI, BCS, the IEEE, the AAAS, and the ACM. He is also the former chief scientist of the Information Systems Office at the U.S. Defense Advanced Research Projects Agency, DARPA, and was awarded a U.S. Air Force Exceptional Civilian Service Medal in 2002. In 2016, he became a member of the National Academies Board on Research Data and Information. In 2017, an advisor to the National Security Directorate at PNNL. And in 2018, was elected a fellow of the National Academy of Public Administration. His talk is titled, Knowing What AI Systems Don't Know and Why It Matters. So I'll hand it over to Dr. Hendler.
Thanks, David. Wonderful to see you again after been a little while. I won't tell the audience how long we've known each other because they think you're younger than that. I also see on the participants list several people whose names I recognize as old friends, but I'm afraid in this modern conjunction of being online, I'm not able to acknowledge you individually. So let me just simply say hi to everybody who I know. And now let me share and get going. Okay. Okay, good. It's actually letting me see my slides today. It doesn't always do that. Okay, so I shortened the title slightly to Knowing What We Don't Know. It's actually a slide deck that's been kind of evolving since an IGCAI keynote in 2016, which was called Artificial Intelligence in the Age of Deep Learning, Watson and the Semantic Web. And I'm gonna have some of the slides that are from that, some from evolving research during time. What I'm gonna try to do is keep it fairly high level. I do have some technical slides in here, and I will be sharing the slides after, but I'm not really going to talk to the details of the learning models and things like that, because that's not really the point. And usually when I've given this talk, I sort of go through a lot of technical stuff about what's going on to get to a punchline. I decided today that I'm going to start with the punchline. There's a famous book called How to Be a Jewish Mother, and it has a wonderful chapter in it called How to Ruin a Joke. And it says, since the punchline's the funniest part, start there. Here, the punchline's not the funniest part. Here, the punchline's probably the most important point about what I think is the biggest problem with current AI systems and are thinking about using them with any kind of assurance in autonomy, right? So this is a one-slide version of an entire long book about a gentleman named Stanislav Petrov. He died a few years ago. I'm sure some of you have heard of him. Petrov was also nicknamed the man who saved the world. Petrov was a Russian military officer who basically was monitoring the panel that represented what their sensors were telling them about US nuclear strikes, nuclear launches. And his job was when the lights went on, he was supposed to pick up the phone, call the Kremlin, and ask them to, initiate mutually assured destruction. So what happened in Petrov's case was one day he's sitting there and lights started kind of flashing on his board, and a few lights were coming on. He later said about 5 of them. And this is one quote from him, but there's a much longer discussion with him. It's all translated from the Russian, and so it's not sort of direct quotes and stuff, but it basically says he had been trained many, many times in many, many scenarios. And in this particular case, the scenario just didn't look like anything he had seen in any of those trainings. So he knew to drop back and sort of use his human knowledge. So go to sort of first principles. And from first principles, he said, when people start a war, they don't start it with only 5 missiles. So he somehow knew that the training he'd seen, the situation he was seeing now, et cetera, just didn't make sense. Fell back into, in a sense, I used to say human intuition, which was his own wording in one of these articles, but really was much more, human knowledge, falling back on basic principles. Why would this be going on? What's going on? How do I reason about it? So in a sense, we've gone through some knees in a curve in AI, right, that are making it so it's possible to even create a center like the one we have here, or for, I'm sure, I know a lot of the AI people over at Hopkins who are doing work in this. I define it, we typically these days call it all deep learning, but in fact, there's really 3 different trends that are all coming together. I'm going to give you sort of a 2-slide introduction of each. And they really, in part, converge because over the course of a few years, they all suddenly became much stronger than they'd been. So deep learning was, sort of, we'd been doing AI and neural nets for a long time, but all of a sudden it seemed that they just had a huge jump in performance. And again, there's technical reasons why that's true. But the one that really brought that to people's attention was AlphaGo. Another one which doesn't have quite as good a name, but and also deep reinforcement learning is, I'm putting that as if it's a subset of the deep learning, just because I don't want to spend time going through all the different variants and things like that. Associative learning is the term I use for what happened in the Watson system. Watson was the Jeopardy playing program. We'll view that in a minute. And it's also very much how GPT-3 and these other language systems nowadays are using. Most of them most AI systems use some combination of a lot of these things. The third one we don't tend to think of in quite the same way, but that's sort of semantic web or now knowledge graphs. Wikidata is becoming very big as a bottom line for these things. DBpedia was a previous version. But what these things did is, everyone knows that all of these systems were made possible by lots of data. But in fact, organizing that data on the web in a way that you could get it, find it, et cetera. So a lot of the breakthrough stuff, particularly Watson and some of the other languagey things, worked by finding lots and lots of stuff on the web and then putting it together. So I'll be talking a little bit about that. So let's look at those quickly. I can talk for the entire hour about this slide, so I won't, but this was, I think by now pretty much everyone knows what deep learning is, deeper neural networks. The real breakthrough in this wasn't really so much having more layers. It was a realization at a mathematical level that of something that had been proved in the late 90s was actually not wrong, but made an assumption. So it was sort of, basically, you can prove that anything you can do with a deep network could be done with a 3-layer network, except that turned out only to be true if you assumed everything was fully connected. And since a lot of the stuff we do now, convolutional, recursive, et cetera, are not fully connected, things like that. It turns out they were able, by putting more layers and changing the architecture as you go down through the layers, you get a lot of power. You've all seen these kind of things. A lot of data was collected, labeled, et cetera. So most of these are still supervised learning. There's some unsupervised pieces going on now and people are looking at putting that together. But by and large, deep learning is still very much, I've trained you on a lot of pictures, texts, language, whatever, and now you're able to do things. So here are, 4 of the very early ones. But the big breakthrough in deep learning was there were a lot of pictures like these that had been being used as a test set for computer vision. And in a period of 2 to 3 years, it went from getting about 50% by, the particular metric being used to getting over 90%. And nowadays it's up in the high 90s. Humans using the same scoring metric get in the mid to low 90s. So in a sense, somewhere around 2012, 2013, you started to see this curve and it started to beat humans. Now, again, there's a lot of argument over if this is the right way to do it or not. I have an entire talk where I just use this one picture up there of the person, the dog in the chair, which reminds me that I meant to say on my first slide, on the cover slide, and these slides will be shared and this is recorded. There's a link to my SlideShare site where a lot of the talks I've given include, sort of the major ones are there. And so that talk with a lot more about sort of this stuff is there. A lot of what was going on in text mining came through something called associative learning. I'm not going to go through this in detail. This is actually an IBM slide about kind of what's inside Watson. I also have given numerous talks on the Watson system. I was one of the, first non-IBMers to be allowed to get my hands on the thing. But Watson obviously did something very impressive in the TV show Jeopardy. It beat the guy on the left, Ken Jennings, is generally acknowledged as the best Jeopardy player of all times, and Watson beat him handily. In my 1-hour talk on the Jeopardy game I used to give, I actually show why it was a lot closer than it looked. But by and large, Watson was exceedingly impressive in 2011 at a task that most AI people at the time would have said is impossible. Watson did not learn and did not use any deep learning. The modern Watson stuff being shared by IBM, sold by IBM, does use more of that. So Watson really showed what's called associative learning. Essentially, the question was associated with many, many features of many, many different things. So it's sort of a search, but then it was filtered through a lot of different techniques in a lot of different ways, some of which were very handcrafted and tied just to Jeopardy, but many of which were fairly generic language things, which are now used as the basis by which a lot of text is brought in, mined, pulled together, and then used to train through deep learning or other mechanisms, things like GPT, things like that. The third one is the semantic web or knowledge graph stuff. Knowledge graph is more or less the term tend to be used where extracted from a lot of data that's either directly in a graph or turns language things into a graph, but also merges graphs. So it's really here what I'm talking about is the ability to have data interoperability. This particular graph is from a Facebook slide shared with permission. And the links here represent, in this particular case, this is sort of an older one, was just mutual likes. But nowadays, it's sort of things like likes, actions on pages, shared ads, things like that. So again, this large graph of sort of who's doing what, knows who, et cetera, is put together. This is what powers the these knowledge boxes you see now in all of the search engines. In 2015, Guha, who then worked at Google said embedded metadata was on 30% of its crawl. In 2016, Peter Norvig gave a talk at the World Wide Web conference where he said it was over 50%. Now, some of you, I see names of people who may remember the old DARPA DAML project, defense, the DARPA agent markup language. I was the program manager of that, and at our kickoff meeting, somebody from a large search company, which I'll tell you was Google, but I'm not supposed to, said, you know, yeah, that stuff's interesting, but you'll never see it as even a noticeable percentage of our crawl. So circa 2015, 2016, I felt like, you know, I can just retire and claim success. Unfortunately, I'm really bad at that, so I keep going. But, you know, this stuff's really out there. Now, is it in the forms we wanted? Is things like that? Again, another whole talk. By the way, it's not just in our systems, it's you know, different search engines throughout the whole thing. So quickly summarizing that introduction, AI has done some way cool stuff. You have deep learning, which really push knowledge, push learning from data with very high quality. You had Watson and this associative learning, which showed that data could be put together from language things with high quality. You had these graph links that let us form new kinds of graphs from the semantic web knowledge graph. And by the way, a lot of the graph neural networks grew out of that, for those of you who know how powerful that technology is. So that's kind of the introduction of saying, you know, there's a lot of stuff out there. It's getting put together in a lot of ways, and that's doing some really impressive stuff. And that's what's caused the breakthrough in AI. If you go to NeurIPS or other such AAAI conferences, you know, most of the papers you'll see will be some modern variant of these techniques. And there are a lot of different names for these. The missing one here is the reinforcement learning, which I really should add, but I keep forgetting. But the real problem is this, right? Right now, putting these things together is very hard, and they all have more or less the same problem. And it's the problem that we don't know how to do what Petrov did. So here's just a simple example of this. This is from a visual query answering, VQA task from some years ago. And you know, you would see a lot of pictures like this, and there would be questions associated with the pictures and their answers, right? So, and then, you know, you would do the typical, pick some sample of those, train on that, validate on another set, test on another set, and the numbers have been going up consistently. And, you know, here's an example. So it says, what is the person holding? And it says, you know, I think they're holding a phone was the top answer. Scissors is the second answer. Bat is the third. Just to be clear, that's bat as in vampire, not bat as in baseball. So it, you know, something shaped like that. But you can see, and it took word association put together with image association and found its kind of highest combinations. And there, again, this has come a while from there, but mostly you'd still see these kind of things. And they do pretty well on depending exactly category. Problem is if you do something like this, right? They were never tested on questions like this. So having been a student of Gene Charniak at Brown many years ago, he was my PhD advisor. Gene was known as the person with a counterexample to everybody's hypothesis. And so when your thesis advisor is really good at poking holes in your stuff, you learn to do it. And what Gene would always try to do is find something outside of what I had been looking at, said, but what about this? And so you know, this is kind of what he trained me to do. So minute I saw these systems, I took a picture like this, and I have lots of others of varying things, but the question is, what is the person holding, right? And you know, these same systems come up with answers, ski poles, right? And by the way, if you look at the numbers and do the analyses, they don't, it's not like I was really sure she was holding a phone before and now I'm pretty unsure it's ski poles. The numbers, when you do the math, don't look that different, right? So there's not really like a threshold where the system could say, I don't know. It very often will get a very high quality answer, very high scored answer in a situation like this. But, you know, this is kind of where you'd like someone to, looking at a picture like this, to say, huh? You know, what are you talking about, right? I actually was giving this talk once back in the days where we could talk to real audiences in person, and not to say you guys aren't a real audience. And someone came up to me after, who was a pilot, and said, you know, the right answer was that the person was the pilot who was holding, I forget what you call the control stick in an airplane. Somebody feel free to post that on the Q&A. But, but, you know, that's exactly the kind of thing. That person looked at this thing and said, okay, I'm going to try to find an answer that makes sense, but it's not a visual answer. It's not something that's immediately obvious from this picture, right? And we have these same kind of problems in all of these different things. So this is an early knowledge graph problem example from Peter Mika, who was at Yahoo at the time. So, and you can find similar things that have been published from other things. This is just my favorite example, which is, you know, when they were generating what's now become the knowledge panes in almost every search engine, this was one of the examples that they showed of something they thought might not be correct. So this is Michelangelo, the artist. Michelangelo, you can see the description, was known as Michelangelo, was a painter, born in 1475, died in 1564, all this great information about him. And there's a picture. Now, it's not a great picture of the actual artist, Leonardo da Vinci, Michelangelo. And there's a lot of reasons why this is chosen as a picture. One of them, of course, is that we don't have a lot of pictures on the web or on any information source of the actual Michelangelo. For some reason, there just weren't a lot of cameras around back then. But the much more important reason from the point I'm making today is this guy Michelangelo hung around with three other people, Leonardo, Raphael, and Donatello. Those of you who aren't old enough to remember the Teenage Mutant Ninja Turtles, those were the Turtles. There's a long backstory on why they were named after Renaissance artists. But these four known Renaissance artists associate significant, you can't find a graph of knowledge about this stuff unless you hand curate it to get rid of this, that knows that, you know, this very tight cluster is somehow different, even though it associates well with other things than Renaissance artists. It's still one of the tightest clusters of anything having to do with the Renaissance when you're looking at the web, because of course the modern web is full primarily of things having to do with what's out there in the world, right? And again, there's lots and lots of other examples of this, but starting to get to what can we do about it, I'm going to go very quickly through a few examples of some things we've looked at in my research group. There's a whole growing field of neurosymbolic, which supposedly is solving some of these problems. And I'm not going to get into too much about that today, except to say that that's still fairly low level. This is trying to get to kind of a higher level. So this is an example I've been using for a while. It was generated originally by one of my students, Matt Clowan, who's now at AFRL. You look at this picture and say, what is the relationship between this man and this woman? And, you know, we can come up with some things. And actually, it's interesting. I've done this with a lot of different audiences, and depending on the age of the audience and where we are, I get different answers. But an AI system that was trained up on this was, you know, is called deep learning with scene graph and relationships This was some of Matt's work that eventually became his thesis work. This was an early version. And there's a lot of other things. This is how sort of the state-of-the-art VQA was working at the time. But these systems kind of generate some kind of scene graph. So again, the system came up with a woman wearing a dress that is blue is next to a man who is wearing a shirt that is white. You know, that's not terrible. But the problem that Matt pointed out is if I change the picture just a little bit, the system still comes up with the same thing. Yet most people in our culture looking at this picture, seeing this version and seeing that person in the back in the long white dress, immediately decide that this must be a wedding. And if it's a wedding, that puts this information somewhat differently. So that's all of a sudden what becomes a very high probability is that's the groom dancing with his mother. Now, we can also override that in a lot of ways. So, excuse me. So, you know, so one thing we could say is, why don't I train on a bunch of wedding pictures now? Okay, so if I've added a whole lot of different weddings to it, now suddenly it starts to see that. But notice that everything I add will cause me to have a lot more stuff in the training sets. As another example, supposing I know that the groom is an orphan, okay? Now you would have to know that, you know, it can't be his mother he's dancing with using some other kind of information. So again, I would either have to add some way of adding that kind of background knowledge. I'd have to add some other things. Here's a much more realistic system. This is actually something one of my students is working with one of our imaging people in our medical imaging group, looking at some of this and not so much identifying the tumors anymore as trying to really generate a explanation. But without going into any detail, essentially, most people, most systems, and most AI systems that were trained on this stuff, so this was actually from a set of state-of-the-art image testing and where mistakes were made. So this is one mistake that was made. This thing here that I'm circling, something you can see my mouse, where the white arrow is pointing, is almost always identified as a potential lung tumor. However, this particular image is from a woman who had a mastectomy. So the minute you know that, that's like saying the groom is an orphan. It means the most likely explanation cannot be true because you can't have a tumor in something that's not there. So it must be something else. And when you drop to the second best answers, or when you know it's not a tumor, and it turns out, again, I don't know the medical details, but the fact that the shadow is sort of where it is changes the story. This is a more complex version of exactly the same thing. This particular tumor is often missed for reasons that I barely understand. But what you need to be able to get this is exactly that kind of scene graph I talked about before that says you need to know that this is what's under which, what's over which, what's next to which. So you need some way of generating that and then reasoning over that to know that because that graph has this feature and not this other feature, essentially that the bright area is in a particular place, that may be one of these kind of tumors. So again, real world example. What are we doing about it? This is sort of the final slide from from Matt's work. And I'm not going to go through it, but essentially what Matt did was added to the knowledge a fairly simple ontology, a food ontology we had taken. And what was able to happen now is that we could not only add the things it could see, but we could add to the training set those things that were entailed by the things it could see. So again, using, you know, standard description logic-y type stuff. If you look at this picture of a pizza and realize it has meat on it, then you can say this is not a vegetarian pizza, or this is a meat pizza, depending reasoning. And he had much more complex examples of it. But notice that that's not an image feature, right? That's something where you have to take the image features and reason from them. And a better example of this would be something like he was able to do things like say, does this photo have garlic in it? And his thesis trained this against the state-of-the-art systems that didn't have this, and showed that he got significantly better VQA performance because it could do this little bit of extra reasoning. And since then, he's gone on to add more. Here's a couple slides from a much different, much more technical talk. I'm just going to show you, blitz through these very quickly. But this was some work done by a student named Bassem Matni. Bassem went to IBM for a few years, is now at Arizona State University decided he'd like to be an academic, so he's back as a postdoc. But essentially looked at that same kind of stuff Matt was doing, but in a different context, learning to reason. For those of you who know the semantic web stuff, you know that we base a lot of stuff on RDF graphs and then on ontologies and sit and reason about them. And Bassem came to me and said, for my thesis, I want to use deep learning to learn RDF inferencing. And I, being a good advisor, knowing that that would never work, told him, sure, go ahead. And he came back a couple months later and showed me it worked, which drove me crazy. And we spent a long time working on what was going on. And, basically what he ended up with in the first pass was something that took correct knowledge, made correct inferences, and they were not terribly different than the inferences made by, standard reasoners. But of course, that's not really a publishable result. We found a worse way of doing something we already did. So I said, what's really the big difference? He said, well, the learning systems are noise resistant. So his doctoral thesis was on noise resistance. Found a lot of real examples. So for example, this is something in DBpedia where something has been named as both a place and a person, right? And in handcrafted knowledge, we could say something like things aren't people and places, but we wanted this, the question was, could the system really learn which were correct inferences and which weren't? So if you throw this into a logic system, don't have sort of all of the details of all the things that could go wrong, then it would make the assumptions, it could not make the assumptions that all of the things that come from being a place are true and all of the things that come from being a person are true. But once you say something is that the United States is a person, then you're making a lot of improper inferences. So when your data is noisy, right, knowledge-based AI systems have a lot of problems. Deep learning is good at that, but of course not at making the inferences. So he put these together, came up with this very, standard, nowadays it's standard, at the time it was a little more complicated, but, encoding of what we knew, turning that into graphs, using those graphs to do things. There is a journal article on this stuff that you can find. We ground truthed it against actual, using rule-based reasoners for which the integrity constraints had put on, so we could do it at scale. Did it for artificial domains like the, let me skip that. So, we could show the difference in accuracy between, for noisy data between the trained system and the logic system. So in other words, we took inferences that should not exist from noisy data that had been introduced, and sure enough, the AI system was not learning, because again, it was just not seeing among the regularities the things that were anonymous. That's not the word I want. The things that were anomalous. We again ran a lot of different things. Some of this stuff was very hard to do about, did some things, but took real world examples. So from, took some results. These were scientists, and it turned out that, when you take this set, we did it for standard semantic web reasoners. And so the system did better, okay? But there was still a problem with this, right? Occasionally there was something where the system ruled out that was correct. So for example, if only one of these people who'd been tagged as a scientist was also tagged as a professor, because actually the way that the early version of this stuff was done, those two were sort of the two different paths up the same tree. So there were very few people, yet scientists who are professors is actually not that uncommon, right? So it just wasn't common in DBpedia. So DBpedia was not learning something that we would have liked it to learn. So good news is it was not learning bad stuff. Bad news is it was not learning low frequency good stuff, which is exactly what KR systems were really designed to do. So sort of summing up some of where we are and what we're trying to do is a realization that this is really in a large way all about context, right? AI learning systems still perform best in well-defined contexts or trained systems, or where the document set is complete. A lot of real world examples of this. Those of you who study autonomous vehicles know that a lot of these vehicles were first developed in California, mostly in Silicon Valley labs and or things coming out of Stanford. Another place where a lot was going on was the Pittsburgh Robotics Lab. Pittsburgh was actually one of the first places to allow to allow autonomous vehicles actually out on the roads. There were some known mistakes, but really interestingly, the first few months, you saw a learning curve where the number of mistakes being made by the system, or so the accuracy went down, the number of mistakes went up. I often give this as a quiz to my AI classes to say, who can tell me why that might have happened? And usually one of the students will eventually figure out that what happened was the weather changed. And so in Southern California, the systems had never been trained where the background was full of snow. And in Pittsburgh, they came over in the summer and were doing very well. And sort of by this time of year, they were not doing as well. In fact, North Dakota became a very popular place for training autonomous vehicles. But now simulators do multi-weathers, multi-things. But again, every time we add something new, the Bride example, we have to add a lot more to the training sets if we're going to use this kind of supervised learning, or we have to find some way to be able to express those anomalies. That's kind of what my student who's now looking at that medical imaging is trying to do, is sort of say, can the system explain its reasoning, not so much for the sake of explainability, but for the sake of us being able to look at that explainability and sort of drop back. So in a sense, the first project I show you was trying to take deep learning and use some knowledge to increase its capability. The second one was sort of trying to learn to avoid noise. Somehow we have to be able to do both these things. Another example that comes up a lot is in training for medical diagnosis, right? The problem is low frequency diagnoses. In a trained system, you need a lot of data. So even systems, we worked with a company that has 300 million patient records, right? Does very, obviously it's out of the park on those things that every doctor already knows, does extremely well on certain kinds of rare cases, say something that happens in, say, 3%, because at that size, 3% is still a noticeable sample. But there are medical things that happen in, 0.01%. And when you're talking 0.01%, the learning systems just didn't get them. But those are the things where people were dying and where the expert doctors did significantly better than the average doctors. And so again, how we build systems that can create that human AI symbiosis, that's a term that DARPA has started using recently, and I love it much better than human computer interaction, because still, I think for the foreseeable future, it's putting these things together that are going to let us really try to break through some of this. So I'm going to stop there. Normally, that's where I would tell the story of Petrov as my punchline, but I told it to you at the beginning. But again, notice what he did was exactly this kind of thing, was able to take information from this training, recognize that it didn't make sense, and fall back on some kind of reasoning. The other thing I didn't talk much about, but I noticed that I'm going to answer one of the questions in the chat before David asked it to me. This part about sort of augmenting the learning with knowledge, that's a big piece of what we're trying to do here. I used the example that I was trying to think of a really good example of an autonomous system in the real world that goes from okay to much better based on a combination of knowledge and experience. And I came up with the idea of a 16-year-old driver, right? Learning to physically manipulate the car is actually significantly easier for them than learning the stuff that's on the driving quiz very often. And once they go out and actually drive, learning that stuff on the quiz is actually right, that, driving 120 miles an hour when you're drunk is probably a bad idea. Those are the kind of things that you'd really like the AI system not to learn by experience, right? You'd like to be able to tell it. And again, lots of examples of that sort of thing. So that's one approach, is augment the knowledge you have with that. But there's a lot of other things that go on in this space too. Another one is, another version of this that people are working on now, we used to call the F equals MA problem, but it's too easy nowadays to call it that. But, you're training up on a lot of physics data, right? You'd really like to put in there something that says, we already know that force equals mass times acceleration, so you don't have to try to learn that. And by the way, if you learn that kind of at 92% accuracy, that's not very helpful, right? We actually believe this to be true, right, for a lot of reasons. So we'd really like you to sort of do it. And what we usually do now is we run the training set and clean it up to put that information in. But, again, that's very hard if what you're going to do is try to be learning in a much more general setting. So again, a lot of what this is all about, and I have another version of the talk that's sort of aimed much more at the symbolic AI world, that says, we must also learn to live in a world where where learning, for many years in KR, people would say, well, a vision system's never going to be good enough that it can actually do this stuff. So we'll just start with a symbolic rendering of the scene and do our reasoning from there. And someday vision will catch up. Well, guess what? Vision is caught up and it's not giving us data that looks like that nice, neat, correct symbolic rendering of the scene. So there's kind of this middle part where you have to figure out what's right and wrong. And that's where this real thrust is. So, a lot of us believe that human plus machine, and that's whether it's human in the loop or human on the loop, for those of you who know those terms from the military, really dominate. Okay, so let me stop answering questions before you ask them. David, I think you were going to look at the chat and.
Okay. Yes. Thank you. That was incredibly informative. Gave us a great overview of some very deep and hard problems in AI and autonomy. And I really thank you for that. So I'll start asking some questions now. So there's a number of great questions on the chat. The first one is, how do you account for bias in training sets? Is it something that you as a scientist or an engineer need to actively look out for, or is it the responsibility of the data set developer?
Yes. It's actually all the above. So bias in training sets is really a problem. And it's not just bias, so I could launch into a long digression about bias, and I've done a lot of work now kind of at the policy level on face recognition. Those of you who know that the ACM's U.S. Technology Policy Council has called for a government moratorium on the use of face recognition in situations that can impact people's civil rights, so particularly, police use and things like that. I chair that committee. I was very involved in that activity. you know, a lot of the problem was bias in the training sets, but there's also other problems that come into these. So for example, just how well do the system, how cameras do spectra of different types turns out to fall into that. Was the system trained? So a lot of the cop systems are making some really bad mistakes, not because they not because of issues that have to do with gender or race or things like that, that also come into it. So those were really the training set biases, but also the fact that most of the pictures they were trained on were pictures taken in a context like this or some other clear context. And then they're being used in a, you know, driving by late at night with a lot of shadows. So again, how do you decide that the accuracy in context one is different than the accuracy in context two? So bias at a mathematical level is one piece of it. Bias in creating the training set is another one. But the third one that still remains is context. How does the system know that the current thing it's getting a high quality answer on is wrong? And again, I have lots and lots of examples of that. Another favorite of mine is if you go out on YouTube and search on man walking an emu, you'll see this cool picture from Australia of a guy who has an emu on a leash and walks it. A lot of AI people hate that because the system always tries to turn it into a dog, right? Because we rarely train anything on pictures of people with emus. And part of why it's a viral video is because it is unusual. However, I have never heard a single human looking at that video say, oh, come on, that's a dog, right? So again, we somehow figure out the difference. And so that's different than training set bias. So training set bias is critical, important. I think it's everybody's responsibility is my fast answer, but it's also not it's a necessary thing for us to deal with, but it's not sufficient.
Okay, thank you. The next question, how much of Dreyfus's classic critique of symbolic AI, which means what computers still can't do, is still relevant for today's deep learning based hybrid systems?
So I took out a couple slides at the beginning of my talk. One of them is called 1990s AI criticism, and Dreyfus's book is the first one shown there. And then the second one is called 2010 AI criticism, and it's the, you know, AI will kill us all from Stephen Hawking. But so I think that a lot of Dreyfus's criticisms are right, but they're much too broad. They were kind of assuming that we would never be at the performance level we are. A better, you know, thing to look at might be Marcus and Davis's Rebooting AI, and some of the other books of that ilk. Some more modern books. I have one called Social Machines, but it's a little out of date. It was 2016, so almost nothing, and it's still correct. I have a great anecdote about that, but we don't have enough time. But there's a chapter in there on computers playing Go, and between when we started writing the chapter and when we got our galleys, we had to completely rewrite that chapter of the book because of how fast AI progress was happening. Yeah. But in a sense, what I've been trying to show you is very much sort of the modern version of some of the Dreyfus and type stuff. But I think Dreyfus did it from a philosophical viewpoint. The Rebooting AI book comes at it from a combination of philosophy, cognitive science, and computer technology. And there's some things going on since then that are also more technical. The kind of emerging field of neurosymbolic AI isn't mostly looking at things quite as hard as what I'm talking about. They're kind of more like the F equals MA problem. But you know, again, that is trying to probe some of these boundaries. But really, so what I'd say is that the underlying argument is still questionable philosophically, and we can argue that as philosophers, but the practical implication, most of the things Dreyfus said a computer will never be able to do, we now have them doing routinely. right? The question is how they're doing it and what's going on inside and what's the meaning of that and things like that. So that would be a very different way to go into that conversation. So I won't.
Okay, great, thank you. The next question. So it says a lot of the standard RDF ontology-based knowledge representation approaches are non-probabilistic. That's great for knowing that orphans don't have mothers, et cetera. You know, but then we need to guess who that woman is likely to be, aunt or godmother or somebody. What do you think are some of the more promising approaches to capture probability in ontologies and knowledge graphs?
A great question. Some of you, of course, know that people are working on what now they call property graphs. Property graphs are, you know, sort of ontology, you know, are kind of knowledge graphs where we can actually put some of the numbers in a different place. And actually, mathematically, they're not that different. You can turn one into the other. But, you know, what I'd say is, you know, I'm trying to think how to put it into a short answer. You know, I used to do a lot of work for the intelligence community. I now just am occasionally an advisor in that space, but back when I lived at the University of Maryland and they were nearby, I had quite a lot of interaction. And, you know, every analyst said what they wanted was probability. But then when you actually dug down and tried to do it, they all had a different idea of what they meant by it. So they did want the system to say it's most likely an aunt or it's most likely a godmother. But, you know, if you say it's 0.83% aunt or 0.62% godmother, that gets a lot harder. So, you know, these are interesting questions and there's a lot going on in that space. But, you know, what I'd say is we still haven't solved some of the basic issues of what does probability really mean. We do know that what's coming out of these learning systems is not probability, right? So in other words, when the system says, you know, 0.8 or, you know, 0.9, that's a cell phone, it's not really that it's a 90% probability it's a cell phone. It's actually it's a mathematical combination of lots of probabilities in a multi-dimensional deep manifold with, you know, random compression going on. And I have colleagues who have taught me those words and I still don't know what most of them actually mean. But we do need to understand uncertainty in that space. Now we have done some work. There's DARPA has a set of programs, Kairos, IEDA, and MAA, that all are kind of trying to share some knowledge representation, quote unquote, or data, you know, having your data include some of the right stuff probabilistically. I chaired sort of a committee on how should we annotate uncertainty on that. But one of the things that we all agreed on very quickly is that you had to separate the thing that would reason over the numbers from the definition of the numbers. So extending RDF with the numbers, there's a lot of good models. And, you know, I really think at this point, it's probably a standardization issue. And the real issue is you don't want to put it on a single link. You want to put it on a graph, subgraph. But the answer to the kind of the deeper question about sort of what do we do with that stuff, I think is really interesting and something I would love to see some really exciting work on. And I know some of the people over on the APL side, I reviewed one of their projects a year ago. We're actually looking at some very interesting thing in that space, but I'm not allowed to talk about it here, nor are they. So you'll just have to get your clearances and go over there.
Okay, great. Thank you so much. Another question. How do you view the relationship between learned models, which is great for tagging and classifying, and contrived systems of rules, policy, laws, rules of engagement that are so integral to our society?
You know, I wish that question had been asked right at the beginning because I would have used that as the title of my talk. I mean, roughly. So I think that's exactly the question. That's a much better statement of what I've been talking about, right? Sort of, in a sense, a lot of the tagging, a lot of what we do in our standard visual and reasoning and all that is just deal with the stuff that's obvious. I don't really have to think much about this thing and doing that with it. But is it appropriate for me to do that during a Zoom conference where blah, 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 you know? Again, that's the stuff that's much harder. We still don't have a very good way of doing a lot of that stuff in traditional AI, but policy and, representing policies, representing rules, things like that, that we're actually okay at. The much harder part is how do you express a rule of engagement? But then we still have this problem of how we put these things together. And I've been talking as if it's you have X and you have Y and we just have to merge them. And frankly, that's been my philosophy about a lot of AI. We tend to get into arguments about endpoint A versus endpoint B, autonomous robots versus completely human. Telerobotics was something I grew up in. And my research group made a lot of progress by saying, let's assume they're both wrong. We put something together which we knew could not be the correct answer. But what we thought is maybe by putting these things together, we'll start to learn what that middle looks like. And that's where I think we are today in AI. I think it's what's wrong with some of the stuff about the so-called neurosymbolic AI is they're not trying to reach out to exactly things like policy, law, rules of engagement, even simple rules of engagement. The fact that the car knows that's a stop sign and the car stops when it sees it are not in any way expressible in such a way that says you stop when you see a stop sign. So if an autonomous vehicle wanted to, quote, teach another autonomous vehicle to drive, it needs to somehow turn those into rules. And again, I took out some slides in the middle of the talk today that I love going into about dogs and cats. And if you look at my, actually it's cats and ducks because those were my kid's first two words. My kid now has a PhD in linguistics, so it's been a while. But, again, if you look at my book or some of these things, you'll see a lot of discussion of this. That's really, to me, what a lot of this is about. And I think, if anything comes out of this, it's more to say the questions we need to be attacking are exactly that space, much more than the answers I'm giving you are correct answers. It's really more to create a research paradigm than to say we know what the answers are.
Thank you. In the last 2 minutes, should I pick the last question or do you want to look through and pick it? Okay, so the next one up on the list is, we know that weddings are places where lots of photos are taken. We know that mother-son dancing, especially photographed. So we're almost conditioned to expect that it is a mother-son dance at a wedding. So it'd be unlikely to see a mother-son photographed at a funeral because we don't photograph funerals in the way we photograph weddings.
Right.
Okay, so my question is, what are the role of expectation in inference, reasoning, scene evaluation, and development, contextualization, et cetera?
Yes, so the piece of work I was talking about by my former student, Matt Klawan, was really trying to look exactly at that. And I didn't go into nearly enough detail. And if you just, Klawann is his last name. And if you sort of search on his papers, you'll find some of this. But really, we didn't quite answer that question because that gets back to exactly what we've been talking about, whether it's via uncertainty, whether it's via rules of engagement, is that the key point is the person who asked this question knows that we don't tend to take pictures at funerals, that kind of picture at a funeral, or that we don't dance at funerals except in rare cases. And we don't like to talk about those much. It's, I'll dance at your funeral is an insult. But somehow we know that. And we want our systems to know that. And if you just give it a lot of training, the fact that it's never seen anyone dancing at a funeral is not a good explanation of why people don't dance at funerals. But without that explanation, you couldn't answer a question. So, okay, what about it's not a funeral? What about it's a cremation? What about it's a sad, a shooting has just occurred out on the streets of Baltimore, right? I mean, again, what I can keep doing is adding a little more knowledge that puts it into a more and more subtle category. And again, I keep going back to that medical example because that's where that really happens. And, whether you call it expectation, background, learning or something, there's still this role where sooner or later you got to pull in some kind of knowledge that either says these things you're saying or learns these things you're saying somehow. So it's able to turn something into a symbolic rule, maybe with probabilities, things like that, because I don't, believe we can do true false reasoning anymore in this world, but we got to do something.
That's great. So there are some more great questions. Unfortunately, it looks like we're out of time. So, I will say thank you very much, Jim, for your presentation. It's been great. I think you've enlightened us in a lot of ways, especially the hard parts about learning and AI, and where it works and where it doesn't work, especially, and what needs to be worked on in the future. So I appreciate it.
Thank you, David. It's great to see you again. Thank you, everybody who's out there, and particularly thank you all my old friends who've probably heard this a million times before, but we're still willing to sit through it again. And keep working on it, because again, the new institute is going to have to deal with these kind of issues if it's going to do what it wants to do, and I sure hope it will. So take it easy.
Thank you.